Conditions for linear regression. In the previous lecture, we had seen what is linear regression, and at the present point, you should be having a decent idea about the concept of linear regression. So, what is the next step? The next step is to understand when to practically use whatever you learned in the last lecture. That is, when should you use the concept of linear regression? On what data should you apply linear regression technique? Tomorrow, if you get any data, because you know linear regression, you do not need to simply apply it there on any particular data. You should know what conditions should be satisfied on a data so that it is perfect for applying linear regression. Or in the other way around, in order to apply linear regression on any particular data, what conditions should be satisfied? So there are 7 different conditions. If these 7 conditions are satisfied on a particular data set, then this particular data set is set for applying linear regression. So whenever you get a data, check for these 7 conditions. If it satisfies, then it's practically feasible for you to go for linear regression. So the first condition says about linearity. So linearity says that the relationship between the dependent and independent variables should be linear. Let us see the equation that we used in the last lecture, y equal to w0 plus w1x. Here, y is your dependent variable and x is your independent variable. W0 and W1 are your coefficients. Why is y called dependent variable? Because its value depends on what is the value of x. But x is an independent observation. It does not depend on anything. For example, if you take the rain prediction example that we considered in the last lecture, we predicted rain based on 4 things. First was humidity, second was temperature, third was the wind speed, and the fourth was air pressure. Here, these 4 things, these are independent variables. These were x1, x2, x3 and x4. These are independent because you are observing the humidity of this particular day, the temperature on this particular day, wind speed on this particular day. So these measurements do not depend on anything. You are independently taking measurements. But what about the prediction? The prediction that you make, that is dependent on these 4 things. Therefore, your prediction or the final solution that you find in the linear regression y is dependent variable while x is your independent variable, right? So the condition of linearity says the relationship between x and y, that should be linear. So in the last lecture we had a very detailed discussion on this, on under what conditions or when do you normally include all the higher order polynomials into linear regression. So in case you are considering higher order polynomials, though you need not strictly go for a linear relationship because though you are aware that you are fitting a curve or whatever. In case you are fitting a linear relationship, in that case you need to see for this particular condition. If you are going for a curve or a higher order polynomial, though you need not follow this linearity condition. So this is the first condition for linear regression, is linearity. Second thing, the second condition is independence of observations. So what is the independence of observation? Just now we saw the equation y equal to w0 plus w1x. Here y is the observation or the predicted value. The independence of this predicted value says that your prediction in this particular scenario should not depend on what were your predictions in the previous scenarios. For example, if you are predicting the percentage of rain as a function of we saw 4 things: humidity, temperature, wind speed and air pressure. If this is the condition, then the prediction that you are making today should not be dependent on what is the prediction you made yesterday. today's prediction should be purely dependent on what is today's humidity, what is today's temperature, and so on. This is what you called as independence. And what is the importance of this? Let's say you prepared a model. Let's say you trained this model in order to predict rain. If you give an input, this model should be able to give you an output, that is 30% chances of rain today or 40% chances of rain today. This output, this model should be able to provide based on what? Your input is this: humidity, temperature, and so on this particular day. At this point, the model should not be asking you what was your prediction on the last day. That dependence should not be there. That is what you call as independence of observations. So we are done with the second condition that you have to check for linear regression. What is the third condition? Third condition is homoscedasticity. It is homoscedasticity. What is homoscedasticity? This condition says the variance of residuals should be constant across all levels of independent variables. First thing, we already know what is independent variable, that is x in our equation, y equal to w0 plus w1x. Your x is your independent variable. Across all the values of x, let's say across all the values of x, your residuals, what are your residuals? Residual is your y minus t, where y is what you found out using your linear regression and t is your actual target. That is, let us say you're predicting rain. So from your data, you know that the prediction for these particular parameters was, let's say, 35%. And you, from your linear regression, derived it to be 33%. So the difference between these two, that 2% is your error. This error term is called as residual. So y minus t, that is the residual. Homoscedasticity means the variance of these residuals should be uniform across the values of x. Let us say you are plotting a line here. These are the points, and for these points you plotted a line like this. Here if you see the error terms, they are varying uniformly across the range of x. That is, if you see this part of the line, here also the error terms are of similar value. If you see here as well, so they are varying uniformly. In other terms, if you plot the value of x with value of y minus t, that is residual, this plot should be uniform. This is what is meant by homoscedasticity. Here, when I say uniform, it need not be strictly uniform. Roughly, it should be uniform. You won't have data that is strictly uniform in order to do a regression problem. So this is homoscedasticity. The fourth point says about normality of residuals. Normality of residuals. What is normality of residuals? This says the error terms or the residuals, they should be normally distributed. What is a normal distribution? It is a bell curve around 0. That is, the center would be 0 and there would be a bell curve. This is a bell curve. What is the importance of a bell curve? Here this means this is your residual value. So y minus t, this is your residual. This means most of the values of your residual is 0. As you move away from 0, you will see less and less number of points. That is, if you are plotting a line like this, most of the points should be very close to your line. That is, almost all your points are close to 0. As you move away from 0, the number of points would reduce. There will be less number of points which are away from 0. In case, that is 0 in the case I am talking about error. That is, for the point that is very close to line, error is almost 0. For the point which is a bit far from line, error is larger. So I am saying that most of the points will have 0 error or very small error. Most of the points are here. As you move away from 0, there will be less and less points, which means the points with the higher y minus t values, they will be very small, very less in number. And the values with y minus t values close to 0, that would be very large. So normal distribution, this is the behavior of any real-time data set. That is, you take any real-time data set, let's say you consider height of all human beings, you will see that it will form a curve of this kind, where this will be the average height of a human being. So most of the people will have a height around this value. Here you will see most of the values. As you move to very smaller heights, there will be very less people. Same, if you go to very larger height, there will be less people who are really tall. This is true for all real-time data. That is, if you see the running speed of all human beings, most of the people will be in an average value, which is the average running speed of a human being. Then there will be one Usain Bolt who stays here, very, very large running speed. Similarly, there will be one very low running speed. So this is a normal distribution. So what is our condition? The residuals, that is y minus t, the error terms, should form a normal distribution, which means almost all the points should be very close to your line, and there should be very less points as you move away from your line. In case of linear regression, let's say you are plotting a line. Let's move on to the fifth condition. The fifth condition says no perfect multicollinearity. No perfect multicollinearity. Multicollinearity. What is multicollinearity? This means the independent variables, they are not highly correlated with each other. That is, in your equation y equal to w0 plus w1x, in this equation, what is the independent variable? X. Let us say you have multiple independent variables, w1 x1 plus w2 x2. This is not x square, x2 plus dot dot dot. So in case of your rain example, rain was dependent on humidity, temperature, wind speed and air pressure. So if let's say your temperature is dependent on humidity and air pressure, just assume that your temperature is totally dependent on humidity and air pressure, which means using humidity and air pressure you can derive the value of temperature. If that is the case, then the value of temperature is redundant for your calculation. This is called perfect multicollinearity. If this relation is uniform, it is called perfect multicollinearity. That is, one independent variable can be expressed as a linear function of some other independent variables. In that case, this particular variable is a waste for you. So such data should be avoided. In simple terms, very simple terms, if you, let's say you are taking some data which has time as a value. Let's say this is a point A, this is a point B, and there is a point C in the middle. T1 is the time taken to reach from A to C. T2 is the time taken to reach from C to B, and T3 is the time taken to reach from A to B. If you are given all these three values as independent variables, T3 is equal to T1 plus T2, because time taken to reach from A to B is time taken to reach from A to C plus C to B. So T3 is redundant, and this is perfect multicollinearity. That is, T3 is uniformly, linearly dependent on T1 and T2. In this case, this is perfect multicollinearity, which means you should avoid this value data T3 altogether. Your data should not have any perfect multicollinearity. Let's go to the sixth point. The sixth point says there should be no autocorrelation. No autocorrelation. What is no autocorrelation? This means the residuals are not correlated with each other. See, for each conditions, you need to see on what these conditions are applied. Is it on the dependent variable? Is it on the independent variable, or on the residuals? So this particular condition is applied on the residual y minus t. There should be no autocorrelation. That is, the residuals, they should not be correlated to each other. So in simple terms, I can say like this, that the residuals should be independent of one another. That is, your error term in one observation should in no way be related to the error that will occur in some other observation. Let us say you are having some time series data. This is time 0, time 1, time 2, time 3, time 4. So here if you plot the error term y minus t, this should not form any particular pattern. Let us say there is a pattern like this. This means at time 0 you are having less error, and as you move forward in time 2 you have more error, time 3 you have even more error. So there is a relation between, there is a correlation between your error terms. This should not happen. Over the time your error term should be uniform. This is autocorrelation. Between your error terms there should be no correlation. Let's see the seventh point. Seventh point is about no outliers. No outliers. What is no outliers? This says normally in your data set, it would so happen that there would be some data which are outliers. That is, if you plot a line like this, let's say based on these points, you made this plot. If it so happens that there are outlier points standing here, let's say there are 3 points here. What will these 3 points do if you use it for training? What these 3 points do will, when you plot the line, your line will be a bit plotted towards those 3 points. And what is the result? Your actual line should have been this only, because almost all your points are according to this particular line. But because you have 3 lines here, they try to make your point come towards them. And these are outliers. The point is they have very large error. So this will cancel out the power of many other points which have small error, which means your line will move towards this. And this is going to destroy your complete model. So what do you want to do? Whenever you get a data, see if there are outlier points and remove those points. Remove those points before you start training. Because mostly what happens is outliers creep into data because of some error while collection of data. Or maybe let's say it was collected by some person, and instead of writing 30 he unknowingly wrote 300. So all other values will be, let's say, 31, 29, 30, 28 and so on. Suddenly you will have one value 300 which is an outlier. This will totally destroy your model. So what you have to do is you have to remove the outliers before proceeding with the model. So these are the 7 conditions that you have to see for. The first condition was linearity of relationship between dependent and independent variables. The second one was independence of observations. Third one was homoscedasticity. And the fourth one, normality of residuals. Fifth one was no perfect multicollinearity. Sixth one was about autocorrelation. We said there should be no autocorrelation. And the last one about outliers. We said there should be no outliers in the data. So if these 7 conditions are satisfied, then you can go for linear regression. In this case, the data is suitable for linear regression. So once you have this practical idea along with the conceptual idea of linear regression, it will be helpful for you in modeling, preparing certain models, right?